Dear students, in the previous class we have discussed in detail how to determine confidence interval for a population mean mu when population standard deviation sigma is known. The procedure was based on the assumption that the variable under consideration is normally distributed with the mean mu and variance sigma square, so that x bar is normal with the mean mu and variance sigma square by n, so that Z is equal to x bar minus mu by sigma by root n is standard normal. So we used the standardized version of x bar, namely x bar minus mu by sigma by root n, to construct the confidence interval for mu when sigma is known, where sigma is the population standard deviation. But what we do if sigma is unknown? Sigma is unknown. And remember this, in most cases population standard deviation, population variance and hence population standard deviation is unknown. Then we cannot construct confidence intervals using Z. In the previous class, the confidence interval for mu was x bar plus or minus Z alpha by 2 sigma by root n. If alpha is 5%, we have 95% confidence interval for mu as x bar plus or minus Z alpha by 2 sigma by root n. This procedure is valid if and only if sigma is unknown. So, if sigma is unknown, as is the usual case, we cannot use the standardized version of x bar to construct confidence intervals. The best we can do is estimate the population standard deviation sigma by its sample counterpart S. Estimate population standard deviation sigma by sample standard deviation S and replace sigma with S. Replace sigma with S and conduct the confidence interval procedure based on the resulting variable, namely T is equal to x bar minus mu by S by root n. So sigma is replaced by S and our confidence interval procedure is based on the resulting variable T. T is equal to x bar minus mu by S by root n instead of sigma by root n. And this T is known as the studentized version of x bar. This is the standardized version of x bar, whereas this quantity is the studentized version of x bar. So we use the studentized version of x bar to construct confidence intervals. And remember this, unlike the standardized version, the studentized version of X bar does not have normal distribution. The studentized version of X bar does not have normal distribution. In 1908, a very famous statistician, William Gossett, determined the distribution of the studentized version of X bar. William Gossett determined the studentized version of X bar, and this distribution now is known as students T distribution. Students T distribution, or simply T distribution. So this is the studentized version of X bar. It is known as students T distribution. It was introduced by William Gossett, but it is known as students T distribution because the company where William Gossett was working prohibited its employees from publishing papers. So he used a pseudonym student and published papers using this pseudonym student. So the name students T distribution. And remember this, in applied statistics, for hypothesis testing, we use T distribution in most cases rather than Z distribution, because in most cases the population standard deviation will be unknown. Now we have to see the properties of the T distribution and the T curve. We consider the properties of the T distribution and the T curve. Remember this, there is only one standard normal distribution, that is Z 0, normal with 0, 1. Only one standard normal distribution. But there are different T distributions for different sample sizes. And we identify a particular T distribution by its degrees of freedom. We identify a particular T distribution by its degrees of freedom. And for the studentized version of X bar, degrees of freedom is n minus 1. But this is not the only degrees of freedom. For T distribution in other cases, we have different degrees of freedom. But in the case of the studentized version, we have n minus 1 degrees of freedom. Remember this, T is equal to X bar minus mu by S by root n. We have defined the degrees of freedom in detail in a previous class, and as an easy way to remember, we define degrees of freedom as n minus k. K is the number of parameters estimated. For the T distribution, we use the sample standard deviation, and for calculating the sample standard deviation, we have to estimate the sample mean, because S is equal to root of sigma x minus x bar square by n minus 1. Since x bar is already calculated, we have n minus 1 degrees of freedom here. We will consider cases with the different degrees of freedom when we consider what is known as the regression analysis and the like. Now, the studentized version has n minus 1 degrees of freedom. Also, the curve associated with a t distribution is known as the t curve. And unlike the Z distribution, we have a large number of t distributions depending on degrees of freedom. Let us see how. 0, 1, 2, 3, etc. Minus 1, minus 2, minus 3, etc. Then for degrees of freedom, now, as an example, if our degrees of freedom is 30, this is for degrees of freedom is equal to 5. This is for degrees of freedom is equal to 1 like this. So we have a family of t curves associated with different degrees of freedom. Unlike Z standardized version of X bar, studentized version has many t curves or many distributions depending on degrees of freedom. So depending on the sample size or degrees of freedom. Now let us see what are the properties. Like the standard normal distribution, area under the t curve is 1. And like a normal distribution, it is symmetric around 0. So expected value of t is equal to 0, as in the case of expected Z is equal to 0. Expected t is equal to 0. And a t curve, like an Z curve, extends infinitely in both directions, approaching the horizontal axis but never touching it. Approaching the horizontal axis, the x-axis, but never touching it. Third, as I said, it is symmetric around 0. And as the number of degrees of freedom increases, t curve increasingly become a standard normal curve. The shape of the t curve is almost the same as the shape of the standard normal curve. This is given by the fact that expected t, like expected Z, is equal to 0. Variance of Z is equal to 1, whereas variance of t is equal to k by k minus 2, where k is the degrees of freedom. Now, as k is equal to 10, it is 10 by 8, 1.25, not equal to 1. When k is equal to 30, it is 30 by 28, 1.08, not equal to 1. When k is equal to 100, it is 30 by 98, is equal to 1.02, almost equal to 1. So as you can see, when the degrees of freedom is 98, so when the degrees of freedom is 100, k is equal to 100, there is no difference between, or there is not much difference between t and Z. That is why we used to say that as the sample size is very large, t curve approaches the standard normal curve. There is no much difference between t curve and standard normal curve. Now, just as using the Z curve, just as using an Z table for finding out the probabilities under Z curve, we have the table to determine probabilities under T curve for different degrees of freedom. And this table will be available with all the books and also available in all the softwares. As an example about how to use the T curve, let us suppose that degrees of freedom is equal to 13, and also assume that alpha is equal to 0.05, and or we can say T is equal to 0.05 is 0, the T value is 1.771, 0.05 here. For degrees of freedom, 13, only 5% of the T distribution lie above 1.771. You can just going through the tables of T values, you can easily find the areas of T distribution beyond specific values. If degrees of freedom is 20, T is 2.03, 5%. It is like that. For degrees of freedom, if you give a different degrees of freedom 8, all these values are given in the T table. You just go through the T table and use it. We will consider examples later with the concrete examples. So remember this, as the degrees of freedom or sample size increases, T increasingly become the standard normal distribution. So for, as one author says, for degrees of freedom greater than 2000, there is no difference between T curve and Z curve. So we can use either the T distribution or the Z distribution for confidence interval construction and hypothesis testing. Only when degrees of freedom is very large, that is it. But remember this, T distribution is based on the assumption that population standard deviation is unknown. So naturally it is better to use T distribution if population standard deviation is unknown, whether the sample size is small or large. If population standard deviation is known, we can use Z distribution. So for practical applications, T distribution is extensively used as sample size will not be very large and as population standard deviation is generally unknown. And we will see examples of how to use T distribution when we consider confidence interval construction in the next class using T distribution.